I want to talk today to Dr. C.Walton Lillehei. Dr. Lillehei could be called the father of modern-day cardiac surgery. Denton Cooley once said, Walt Lillehei brought the can opener for the cardiac surgery picnic. He was referring first to cross-circulation techniques and later to the simple disposable oxygenator, the DeWalt oxygenator developed at the University of Minnesota in 1955. Dr. Lillehei shared this information from visitors from all over the world. The basic knowledge needed to start a cardiac program was available at the University of Minnesota at that time and began the burst of activity in cardiac surgery during the 1950s. He trained a whole generation of cardiac surgeons at both Minnesota and at Cornell. I want Dr. Lillehei to tell us about the origins of cardiac surgery in Minnesota in the 1950s, but first I want him to tell us about his parents and growing up in Minnesota. So you left Italy?
Oh, we left Italy then left Italy about the first part of October because I landed back in the United States about the middle of October in 1945, and immediately was discharged. They said, do you want to join the reserve? And I said no, because I had a very good experience in the Army. I was a lieutenant colonel by that time, commanding officer of one of the 33rd Field Hospital. But I had noted during my months in the Army frequent conversations where doctors had joined the reserve during the mid-war, the years between World War I and II. They were called to service at a lower rank than the people were coming in. So that turned out to be well. Otherwise, I would have been called to service, 1950, I guess, was the Korean War.
Korean War, yes.
But anyway, I was in the end of my residency at that time, so I went back to the United States and to my home in Minneapolis. And about 2 days later, I went over to see Dr. Wangenstein, who was chairman of the Department of Surgery. Well, I'd known a little bit as a student, but not really well, and I had written him once or twice during the war that I intended to return for surgical training. And he wrote back several times and was always very friendly, and said, by all means, do that. So I went over to the surgery department that day. I didn't even have any civilian clothes yet, my uniform. And the secretary said, oh, you're returning for training? And I said, yes. He said, well, you have to see Dr. Barco. Dr. Barco was professor there at that time, later became a very close friend of mine. At that time, I did not know him very well. I'd known him a little bit as a medical student, but Barco was very friendly and said they've organized a wonderful course for returning veterans. It was going to be 9 months long, and he reeled off a number of the lectures that were going to be imported, as well as local people, to lecture on various subjects to bring us up to date and the basic things we perhaps forgot, and also the latest developments. I sort of had a long face, I guess, and he said, well, what do you think about that? And I said, well, I don't think much, Dick, Marco, and but I'll think about it. But because I had no thought of going any other place, because I had admired Dr. Wangenstein's record and his lectures and so on when I was a medical student. And I went, as the way out of the office, Miss Jacobson, a longtime secretary who I'd known as medical students, you know, secretaries very well to get your rotations and things like that. And she said, well, how did it go? I said, oh, not very well. He wants me to take that course. Oh, she says, that's a marvelous course, but I tell you, why don't you stop in and see Dr. Wangenstein? This was a Tuesday. He sees, Thursday he doesn't operate, and he sees his residents and doing experimental work and other duties that he doesn't have time during the operative days, and I'll make an appointment for you. She said, it'd be late in the day because you've got a lot of people. It was about 5 o'clock on a Thursday, it's 2 days from the following Tuesday. So I was there, and he greeted me with a very friendly conversation and asked me about some of the doctors that he had been in Minnesota during the entire war, who he had known, been in the service, and we conversed for about 10 minutes. And then he said, Walt, when do you want to start? I said, the residency. I said, right now. He says, fine. Picked up the phone and called his senior resident who was making rounds on one of the stations, and he said, I'm going to send you over Colonel Lillehei at that time, or Dr. Lillehei, and he's going to join us. So that took care of the residency problem. And about a week later, I have to tell this part to complete the story, my longtime friend John Lewis, we had become separated in England, and we were together as far as England, but he was stayed in England, landing in June 6th of the D-Day landing, June 6th of 44. He came back and he called me in the late afternoon and said, I just got back yesterday and I went over to see about a residency, and I saw Dr. Barco and he told me about this course. And like John Lewis, like I was, we're not very happy with the course idea. I said, John, I'll tell you what happened to me. Make an appointment to see Dr. Wagenstein. He didn't happen to have the good luck to be scheduled. Said, make an appointment on the next Thursday, and I'm sure he'd like to see you because he knew Dr. Lewis. It was Dr. Lewis had interned at the University Hospital. I had interned at the City Hospital in Minneapolis. But anyway, same thing happened. He greeted Dr. Lewis warmly, asked him when he wanted to start. So we both, close friends, got started, and that's important in a way because we'll speak about open heart surgery, I think, in this interview. And John Lewis actually was the first person in the world to do a successful open heart operation. I had the pleasure of assisting him in September 2nd of 1952. And both of us, to retrogress a little bit, I think this was moving ahead to the time we had finished our training as surgeons under the tutelage of Dr. Wagenstein. And both of us had decided that one of the fields that was the most promising for investigation, and there was a strong element of investigation associated with Dr. Wagenstein's training system. It was unique really in the United States or maybe the world, but one of the important successes in this early development of open heart operations was, we appreciated, Dr. Wall, originally that you needed some material other than glass or rubber. Most of the IV and intravenous equipments in the hospital and anything that attached to blood was glass or rubber. And we needed some a new plastic called polyethylene. And we found by chance, through just a conversation, that there was a company in Minneapolis called Mayon Plastics, Mayon, M-A-Y-O-N, and they were working, they were an independent small company. As a matter of fact, the president turned out to be one of my high school classmates. I had lost track of him. He was graduated from chemical engineering at the university. He had established this company to make plastic for the milk industry because they were using separation of milk and cream with pumping the milk or cream with a pump that massaged the tubing. It didn't contact the milk or cream, but they wanted a material that could be heat sterilizable, which polyethylene was, and inexpensive enough to be discarded. That was ideal for our use. So we quickly contacted Mr. Ray Johnson, who was president at that time, and he was very cooperative. And as a matter of fact, it turned out to be very lucrative because in quick order, as his word spread around the United States and the world, he was selling more Mayon plastic to the surgeons than he was to the creamery industry. So that was a ideal source. And that.
Did you use some of their defoaming techniques too?
Yes,
from the
we
milk
used the
industry?
Corning antifoam A in that transverse. So the original bubble oxygenator, the very first, had a vertical oxygenating chamber about 1.5 to 2 feet, and a transverse chamber which was about 1.5 foot and bigger caliber, and that was coated with antifoam A that had been autoclaved on, baked, and the antifoam immediately evaporates, bubbles when it contacts them. But that wouldn't have been enough. The helix reservoir was the final protective agent that prevented.
And that early DeWalt oxygenator and pump used a Sigma motor pump rather than
Yeah, we used a
pump.
Sigma motor that was a cam-operated pump that massaged the tubing from the outside. And
So it had a limited flow rate, I suppose.
well, it was adequate for us.
Yes.
You could you could get a bigger flow with a bigger tubing through the pump, but there was never any limitation of flow with that apparatus. The main attraction was that it was operated by a single motor, so you don't have to calibrate, but multiple cams, about 8 on each side, massaged the blood in opposite directions, and all you had to do was calibrate that exactly before surgery, because you didn't want blood piling up in the donor or vice versa in the patient. But if you calibrated that exactly, you didn't need a flow meter. We experimented a little with flow meters, but they were no asset at that time. Calibration was the secret to having the blood flow equal.
And then that idea progressed on to the sheet.
Yeah, well, in 1956, this was 55, when we first started the bubble oxygenator, and for about 2 months, we used the bubble oxygenator for the simple intracardiac cases and reserved the cross circulation for the more complex, but the bubble oxygenator quickly demonstrated its efficacy, and we stopped completely the cross circulation then and went on with the bubble oxygenator. And by 1956, Gott and DeWalt and English surgeon named Paneth and Raymond Reed were all working on this problem, had developed the DeWalt Lillehei bubble oxygenator into a sheet of plastic, which is the same principle, but it could be manufactured commercially and shipped sterile and hung up and primed and ready to go. And we patented that for the Minnesota, gave the patent to the university, but licensed it to games with T.
I've forgotten myself. I can't say. I don't know.
We licensed it to a commercial company in Morton Grove, Illinois. I'll think of it in a moment, but they made these for the whole world and for 4 or 5, 7 or 8 years. And by that time, of course, a number of people, was so simple, they could make their own, and they got into the field, although I don't think any of them is quite as good as the original sheet oxygenator in the beginning. And then the next milestone that occurred about 10 years later was the use of a disposable membrane oxygenator. And we developed that also in Minnesota with a surgeon worked a lot in physiology named Arnold Landé. And these days, I guess almost all the surgery, although a few are done with a bubble oxygenator. The membrane oxygenator is just an added safety, and it's simple and disposable and more expensive than the original ones, but really inexpensive as medical devices go at this time.
I wanted to ask you also, at that time, patients after VSD repair, some had surgical heart block, and so you began having to use external pacemakers.
Well, I think that's one of the things that we should take up. One of the important bonuses of open heart surgery was the development, for the first time, a effective treatment for a complete heart block. A complete heart block in the early 50s or mid 50s was considered a very rare entity. A few patients in terminal heart failure developed block before they died, and a few infants were born with complete block, and the outlook for them was not very good, and there was no real knowledge developed for treatment of heart block because it was thought to be rare and unimportant. The people who were terminal heart failure were terminal from fundamental other reasons, and heart block is, perhaps people listening to this won't understand what we mean by heart block. Heart block means the ventricles, the connection between the rhythm of the atria and the ventricles is interrupted. And when that happens, the ventricles, the pumping part of the heart, beat at a very slow rate, 20 to 30, and that's compatible with life, but the problem is very frequently that ventricle contractions just stop, the patient dies. And that was happening in thousands of patients in those days, but they all had coronary artery disease. And so the heart block was just thought, when they died suddenly, not an electrical death, but an actual death due to progression of the coronary thromboses. So cardiologists did not recognize it. When we first started open heart surgery, it was predicted because the main nervous bundle from the upper chambers to the lower chambers runs right through the ventricle in the very area where most of the ventricular defects occur. And it was predicted by a few that you were going to have, if you were able to work in the heart, I recall being told that you're going to have 100% of this complete heart block. And I knew nothing about it, and very few cardiologists or experts, so-called, at that day knew anything about it, and we just shrugged our shoulders and hoped for the best. Well, the good news, the bad news was, in the first 70 ventricular septal defects we operate upon, mostly with cross circulation and beginning with a bubble oxygenator, 10% of those 70 had complete heart block that persisted. We had a number of complete heart blocks for 5 minutes, 10 minutes, 15 minutes, and disappeared by the time we were done with surgery. But the persistent ones, those 7 of the 70, all died, not immediately, but a couple of days, 3 days, 5 days, week. They did not leave the hospital because the only treatment at that time for complete heart block was things like epinephrine in a drip, or ephedrine given one way or another, and maybe lactate was thought to be beneficial, but the main drug was epinephrine or ephedrine, epinephrine. And of course, we had to administer that by a drip, and pumps were not available at that time. The drip had to be regulated by a screw clamp, and as a result, patients would have a heart rate of about 300. Nurse would screw it down, and next thing you know, it was 0, rested. So that was not very satisfactory. In fact, we had no survivors. We had a few survivors at that time in '55 with a new drug that came on the market for asthma called Isoprel. But Isoprel could not be given intravenously, had to give it rectally or by mouth. And that produced some survivors. I think of the next 13 treated with Isoprel, 7 survived. If you kept them alive, many of them would recover their normal sinus rhythm, and that would be very satisfactory. But if they didn't recover that, they were doomed to death in those early days. So we had a very intensive crash program in our experimental laboratory to do something for heart block, something better. And again, the dog was an ideal animal because you could complete heart block in the dog by just making, occluding the entrance of the blood to the heart, making a small incision in the upper chamber, and put one stitch in the AV canal area. And that took only 30 seconds or so. And then get out, and the dog had complete heart block and was an ideal subject for experimentation. A number of drugs and other things were tried, and we had known in 1950-51, there had been a single case report here from Boston that Dr. Zoll had resurrected a patient who had died in the hospital by applying electrodes to the chest. And obviously that patient had heart block because they started the heart easily, but it took 50 to 75 volts. We used that in our early patients, but it was intolerable because 50 or 75 volts to the chest 60 times a minute is very painful and intolerable, and the blisters develop under the electrodes in short order and infection. So that didn't work. But we did apply electrical stimulus to the heart itself, and the wire anywhere in the ventricle, right or left, very small charge of current, 5 to 10 milliamps, thousandths of an amp is a milliamp, of course, 1 to 2 volts, would drive the heart in block, any rate that you desired by the number of impulses you fed to it. And that was totally imperceptible as far as pain. And that was discovered by several researchers in the laboratory, particularly William Weirich, who was a Markle Scholar from California, and Vince Scott was working on that particularly. I think DeWall helped. As soon as that discovery occurred after a few dogs, then the wire didn't even have to be insulated. It just had to be in contact with the ventricles. I was sort of skeptical that this was going to be a long-term solution because I didn't think we can keep a wire on a moving organ like the heart, but if we had to, we had to, and that turned out to be true. Almost the very next day when we were operating on a patient with high-pressure ventricular defect and had a post-op heart block, it was January 30th of 1957, I called over for the lab, bring the wire over. It was just a simple piece of wire, and we're using the pulse generator, a GRASS called GRASS, that's the name of a man, a stimulator that they used for teaching students that you could plug in the wall, but there's 2 knobs for rates anywhere you wanted within 0 to 100, and the current was calibrated down to 0 to 1 or 2 volts or more, and that was an ideal unit for the pulse generator in the beginning, but it had, and I think we used that in 18 patients, and with the electrical stimulation, the death rate that had been 100% in the early cases and about 40% in the isoprel, the survival rate turned out to be 89%, because if you keep them alive with electric stimulus, the heart usually reverted to sinus rhythm within a month or so. Those that didn't, of course, were another problem. It is at that point, we're using the GRASS physiological stimulator, that I spoke to a young worker that we had hired to help during the intercardiac operations. We did not have much electrical equipment, but what we had always had 60 cycle, and we needed the chest. The electrocardiogram was important in the operating room, even in the early days. We used for a while electroencephalogram, but that was not as important. But the Sanborn pressure measuring was important, that was electrical. So we asked this young fellow, the operating room, the hospital electricians would not go in the operating room during the operating procedure. It was in their contract. So we hired this fellow to come over for heart surgery, and he got our schedule, and he was always available, and he was a big help. His name was Earl Bakken, And one day I said to Earl, you know, this heart block is working pretty good, but we have to plug it into the wall to get the source of the current. And these patients are hindered by the length of the cord as far as movement, and they could not go down to the main x-ray or main lab because if you had to move them, you had to string a cord so they could be stimulated, because if you didn't stimulate a heart block patient, they likely would stop. And within 3 or 4 months, he developed a battery-driven pulse generator. I said one that you could wear on your belt, and we've seen pictures of that, many of you. And that turned out to be the beginning of the Medtronic pacemaker industry. The first pacemakers he made in the garage of his home in North Minneapolis. And we have a nice picture of that in the midwinter of 1958. As I said, the first pacemaker patients with this new technique, electrical stimulation with small currents and a pulse generator, started in January of '57. And we were talking in meetings like the national meetings and writing that this dreaded complication of heart block could be treated more satisfactorily with a pulse generator and a wire to the heart. And when the heart resumed normal rhythm, you could just pull this wire out of the ventricle muscle. And of course, he was getting orders from all over the country. And Medtronic, I guess, as most people know, is a giant in the electrical industry now. They still about half their income is, I guess, pulse generators, but I mean for heart block. But they have many other products, as you know. And I think they have sales last year. Their headquarters is still in North Minneapolis, about $3.5 billion of sales, and I don't know, there's something like 20,000 employees worldwide. So that's one of the big success stories that grew out of the early open heart, because now it was realized, or quickly realized, that many patients were dying and they weren't diagnosing heart block. It was easy to diagnose with electrocardiogram or even listening when the heart went very slow, 20 or 30, chances are you had heart block. And I think there's about 5 million people now around the world living normal life with an implantable pacemaker. That was the next stage, to just implant the...
I was going to ask you that, how long that stage took from the surgical external
Well,
generator.
the first external unit made by Medtronic was in, I think, April of '58, and by 1960, about 2 years.
Very short period of time.
Yeah, well, a doctor in Buffalo, Shardak, and really the...
Gage.
Gage. Gage, yeah.
Shardak and Gage.
Gage.
And Great Batch.
Great Batch is the one I'm thinking
Great
of.
Batch.
Great
Right.
Batch was the really the developer of the unit, because he was a good friend of Manny Villafana and some of the people here in Minneapolis, and he knew about the work with heart block, and he took this same unit, essentially that Robakin had developed, and bedded in plastic, and put it in the under the skin, which is a big advantage. The early ones were not as reliable as you wanted, but they worked very well. And almost immediately, Medtronic bought his use of his patent. And in Sweden, Dr. Senning, who's been a frequent visitor of us in the early days of open heart surgery, also a good friend, was working with a Swedish engineer, and he developed an implantable one that almost at the same time, 1960. With they were using transistorized charged batteries, charge them through the skin. That was a lot of problems. Most people have given that up, but it was one of the pioneers.
Now, during that time, you also got interested in a bileaflet valve, is that
Yes,
correct?
One of the things that there were many things going on in open heart surgery. Of course, I might say word got around, as I said earlier, that people in Minneapolis were doing open heart surgery every day, and the first unit other than Minneapolis was the Mayo Clinic. My good friend John Kirkland, that was only 90 miles south of Minneapolis in Rochester, started open heart surgery on a regular basis in '55. And for the next year or two, we had been doing it since 1952 to '55, and then '55 joined by Mayo Clinic, and another year or two before the next group, which was Dr. Cooley, who had come up and visited me. I think I had the honor of showing Denton the inside of the living human heart for the first time he'd ever saw it, and he's written memorably. He's a very good writer, as you know, and a great speaker. He said it was like looking inside the open heart. He said, like viewing through the gates of heaven, he said. And he had come to Minneapolis in '55 and spent a week, and he didn't try the cross circulation, but he liked we were just starting the bubble oxygenator. I think in that week we did one cross circulation and one bubble oxygenator, and he went back with his colleague in cardiology. I think it was the name slips my mind now, but worked on the bubble oxygenator. But people at Houston, Dr. DeBakey was his chief, felt that this was too simple, and he was cajoling Cooley to try the Kirkland. Kirkland had, with the help of an excellent physiologist named Earl Wood, had modified the original Gibbon machine. It was still very complex, but got rid of some of the problems. It was complex. It had to be filled with a large quantity of blood to make it work, and it could not be cleaned or could not be sterilized by autoclaving, so it was a very difficult machine, but he got it working, and but they were not in the business of supplying them, and somebody were in the business, I think, in St. Louis said it would be $200,000 or $300,000 to repeat this machine. And finally, Denton Cooley prevailed. In '56, he started working with the bubble oxygenator. That was so highly successful, and if you paid attention to physiology, efficient, and even the Mayo Clinic, when Kirkland left to go to Alabama, Dr. Magoon adopted the bubble oxygenator immediately, so it was a much more effective unit, simpler and inexpensive, so it was a lasting contribution, I think.
What was the time that you began working on the bileaflet valve?
Well, the bileaflet valve came about in a period, I might say, to retrogress or return for a minute to the sequence. All of the operations in '55, '54, '52, 52 through '55 in our place, and also '55 in Rochester, were all on birth defects of the heart. Mm-hmm. But in '56, we had enough confidence in the bubble oxygenator, and its capacity was ample to turn to adults open heart surgery. So we began a determined effort and a sizable number of patients, particularly originally on the valves, because valve disease was a very common form of heart disease in adults that we felt we could correct. And so we started early on with valves. I think the first description of annuloplasty in the literature was one by us in 1956 in Journal Lancet. And if you had a valve that was leaking, microregurgitation, and scarred, but still quite pliable, this was a wonderful operation. I think the first 6 of them recovered. Of course, a lot of those valves were not that ample. One of the problems with acquired heart disease was that depending on etiology and the time it existed and a lot of other factors, you could have a tremendous amount of fibrosis, calcium, clots, and destruction of the tissue. So some of the early ones like annuloplasty and other techniques that could repair quite adequately. But by 1957, we were working in the laboratory in the meantime to have artificial valves that were not available at that time to implant. And 57, we implanted the first successful aortic valve, and it was a silicone single leaflet, like a toilet seat, opened and closed. And that was a stimulus to a number of other ideas, and other people around the world were working on it. So there was a lot of designs, but the first really effective implantable cardiac valve came about with the work of Starr, with the ball valve, because it was virtually indestructible. The original ball valves were very durable. They were space occupying, that's one of the disadvantages. But if you could put a Starr ball valve in the mitral aortic area, insert it properly, it restored function very well. And but they had a tendency to develop clot around them, amongst other things, and we were working on several different designs. One of them was the Lillehei caster valve that had a single, well, it was a vitalium or titanium cage. And for the first time, the work of Vincent Gott, who was one of our early residents in Minnesota, at that time had gone on to first Wisconsin and then Johns Hopkins, had been working with a scientist, engineer in Gulf Atomic, and on this new material that they developed for the space program called pyrolytic carbon. It was extremely hard, extremely heat resistant, and it was supposed to be used on the cone of the reentry vehicles, but they found another method where the cone was coated with material that burned and flaked off was better than this impervious material. But this pyrolytic carbon made synthetically was the hardest man-made substance known. It was the only material harder was diamonds, natural diamonds. And that attracted Dr. Gott, and he got acquainted with Bockris, the engineer. They did a series of animals, and of course the wearability of this material was infinite, almost wear halfway through in about 200 years of the leaflets, and halfway through was still a functional valve. The other thing that Gott found when he studied thrombosis, he had a technique for dogs. He could put a little piece of material like a wedding ring, and he put 4 or 5 in the atrium of a dog, suspend it into the stream, and study how quickly it clotted. And he found that pyrolytic carbon was not only the most resistant to wear, but it was most resistant to clotting. And he told us that his publications in the early days were all in obscure engineering journals. As soon as he told us that, and we knew Dr. Gott very well, he spent 6 years with us, we incorporated that in our Lillehei caster for the first time, and that had about 65,000 implants. It was a hingeless leaflet of pyrolytic carbon that rotated freely and hinged. It doesn't hinge on a different hinge. It hinged on a cage, and didn't have a cage. It had hinged on a sprocket system.
Now, you were telling me about the tilting disc and the Pyrolyte and how that evolved.
Well, the pivoting disc, we call it tilting disc also, as it describes it, was very successful. It was the DC3 of heart valves in those days because it never wore out, and it had better flow and better clotting characteristics, non-clotting characteristics than the ball valve, which is still widely used. And this pyrolytic carbon that had been initiated by Dr. Gott and Bockris worked extremely well. And that was going on in the clinical field. And part of our training program by that time, we expanded at Minnesota to 15, 20, even 25 fellows, residents in training on our service. That seems like an enormous number, and it was. But they were scattered off in physiology and even electrical engineering and pathology and some in zoology, all studying various things, and the teaching of Wangenstein, because he felt that the knowledge acquired from other fields was often difficult to get back to surgery or any clinical medicine because there was no interchange. And we had good interchange in that time. And one of the surgeons, so we had a large number of people we could train, but not nearly as many as applied. So I don't know how we did as well as we did, but we were able to attract some of the best and brightest young brains in the world. They didn't look like it when they came. They looked like John Hunter's residents in surgery 300 years earlier. He said they were loud, profane, often addicted to spirits and low company, especially women. They fit that description pretty well, but their later record, many of them becoming world famous authorities like Shumway and Barnard and Christian Cabal and Donald Ross and Levy and Israel and Wada in Japan. Well, start naming them, or South America, of course, Zerbini and Bittencourt, and I'm sure Warden and Cohen. Cohen became chief of surgery in the University of Winnipeg. But get back to our training program. We'd like to have the people, if they did not, some of them came as trained surgeons, had experience in thoracic, even surgery, and they spent a year with us. But the basic program was 4 years at least, sometimes longer. And Dr. Kalki, Bhagrant Kalki, was an Indian from Bombay, and he was on the 4-year program in 1965. He was with us from 1964 to 68. In 1965, he was due to go in the laboratory. They were walking down the hall one day, and he said he was due to go in the laboratory, and he'd like to work on a bileaflet valve. I said, well, why, Bhagrant? There's all kinds of designs around. But he said nobody designed a rigid bileaflet. Vincent Gott had worked on a pliable, flexible bileaflet, but it had problems with wear and flow. But I said, well, the reason nobody's worked on it, because it violates almost every principle we know. It's got a fixed hinge, which is going to wear, and stasis around that is going to promote clot. But at the same time, I'd learned by this time that one of the particular hazards of professors around the country and around the world is when they were approached with a new idea by a young fellow, they had almost a knee-jerk reaction, and without thinking to say, well, it won't work, it's been tried before. And I almost said that, it won't work. I caught myself and I said, well, we'll authorize some funds. Bhagrant was a long name, we called him Ball Cocky for short. I'll authorize some funds and get a bileaflet valve made in the machine shop at the hospital. And I think the first thing is to do is to test the flow. We had an engineering student working with us at that time, Robert Castor, who later became well known because he stayed on and worked in one of the first biological engineers. And he had developed at that time in '55 a very sensitive and durable flow meter, analog pulse duplicator, he called it. I said, have Bob Castor run the flow through and see how it comes out. I didn't hear anything for about 4 or 5 weeks. He came back to me once when we were making rounds. and showed these flow characteristics with this. He had the valve, they were very cumbersome cast iron valve, bileaflet, with a cage on it. And these flow studies were better than the Lillehei caster valve, the tilting pivoting disc, which were used clinically, and one of the attributes of that valve, amongst others, was the flow. I said, I can hardly believe this. We'll make a date next Saturday, and I come down to the lab. I'm not operating on Saturday, and I'd like to see these again. And sure enough, we did that, and each flow with this crude valve was significantly better. And I said, well, we need to work on that. So I worked with him. We got rid of the cage. We refined the structure, and finally by 1968 we had a clinical model, which you've seen, that's very much like the St. Jude valve. Actually, it was titanium though, and 2 leaflets that opened to 60 degrees, and Dacron or Teflon skirt to sew in, and the pivoting mechanism was on the outflow. It was a knee socket type of pivot. It was almost 3/4, well, it was about half open to promote flow around it. And we called that the clinical model. But I knew the CEOs of 3 of the biggest valve companies at that time, mostly in the United States, and described this valve. Can you make it? This before the FDA, of course. All you need to do is to make it, and if you were convinced that it was superior, to use it. So there was no hurdles on that score. That was, same was true with that first pacemaker. We didn't have to get FDA approval, or we'd still be waiting. But they looked at the data, and Dr. Kalki, in the meantime, suggested, as in accordance with our procedure in Minnesota, that he write this up for a PhD degree, which he did. So we had a lot of data on the flow of this in pulse duplicator, studies in animals with angiographic and techniques, and I said in animals, I think, and all being very favorable. But the CEOs all said, well, Walt, we know you, but we like you, but this won't work in humans. It'll wear out or clot. So that valve stayed on the shelf from 68. Kalki got his PhD degree on that date, to that time, yet year, went back to India, where he became chief of surgery in one of the bigger hospitals. Get back to the story, that bileaflet valve remained on the shelf from 68 till 1976. 1976, a good friend of mine, Manny Villafana, who had worked on us with the pacemaker and established a pacemaker company called CPI in St. Paul, right in the shadow of Medtronic, because Manny Villafana and who's the pacemaker? We just talked about
Great Batch.
Great Batch had developed a lithium battery for pacemakers.
Right.
And but nobody was interested in it because the main advantages, which was significant, it had about 10 times the length of a mercury cell, which were being used in the pacemakers. The other big advantage, it did not give any gas off. When a mercury cell discharges, it gives off hydrogen. So if you have a mercury cell encapsulated, you have to have some one-way valve to let the hydrogen out. And that one-way valve was not totally effective and frequently let body fluids into the pacemaker, and that was one of the causes of failure. So the lithium was a big advantage technically, but they'd only been used infrequently by the Coast Guard and some other special places where they had need for a battery, and a searchlight, for example, was not very serviceable, and they had a habit of exploding periodically. So that turned off Medtronic completely. They were presented with this first go-around, and so Manny Villafana, who was a born in the United States of Puerto Rican parents, very low economic status in the inner city of New York, and how he developed is another story. But anyway, he became a very successful developer of new companies, and so he established cardiac pacemakers to make this lithium battery pacemaker right in St. Paul. Minneapolis is the source of Medtronic. And authorities at that time said they won't last a month or two, but the lithium battery was very successful. And very soon all the big pacemaker companies were scrambling to get a lithium battery pacemaker. Well, that leads up to the next step about the pyrolytic carbon in the valve, because Mr. Villafana sold cardiac pacemakers to Eli Lilly in about must have been about end of the 60s, I think, for 136 million, which didn't sound so much these days with all the mergers, but that was a pretty significant sum. And Mr. Villafana then, he was not the sole owner, he was the CEO of the company, but he was looking around for something else to do with his money, and he, with the help of 2 or 3 other advisors, Dr. Nikoloff was the surgeon that trained with me, and a couple of others, and I wasn't in that committee at that time. They had narrowed down. Mr. Villafana said he had picked a field, heart valves. He said he could make a better heart valve like he made a better pacemaker. And they were looking around for what the better heart valve would be. And they decided on this Lillehei technique. And at that time I entered the field, and I said, well, if you're going to make this, this is now 1976, so it's 8 years this valve had been on the shelf. And we sort of forgot about it in a way. I said, with our success with Pyrolyte, make the whole valve out of pyrolytic carbon, the orifice and the 2 leaflets, and open the leaflets to 85 degrees instead of 60, which they had in the experimental model of the Lillehei, or the Lillehei valve. And the pivot mechanism was going to be left the same, but the people that made pyrolytic carbon said they could not engineer a pivot mechanism within the orifice. So the pivot guard was developed. It was on the inflow side of the valve, which I thought was a very wise decision to make it on the inflow. And they could, well, first they said they couldn't do that, but with persistence and determination, they finally, this is Gulf Atomic now making the pyrolytic. That was the only people in the world that knew this material, said that they could make it there. So in 1976, Mr. Villafana established this company, St. Jude Medical, to make this new valve. It was the only product, and the first implantation was October of 1977, and the valve worked beautifully, but most surgeons were skeptical of the design, like the entrepreneurs were. So it took 8 years till took 8 years from 1977 to 85 for the first 100,000 to get implanted. But by that time, the results were so impressive, both in flow, diminished clotting ability, and of course there was no problems of wearing out, that the valve took off. And we had a 20-year celebration, October 4th, which is the date of the first implant at the University of Minnesota. We had that celebration last year in '97, and 800,000 St. Jude valves have been implanted at that point. And of course it's still going strong. There's a continuing controversy, I suppose, but not so much controversy, but research on how to make tissue valves better and mechanical valves better. And we know tissue valves are excellent, particularly for older people, because they do require less anticoagulation, but they do wear out. So the final solution, if there is a final solution, will have to be taken up in the foreseeable future. But the St. Jude valve has become the most successful mechanical valve that's ever developed. And it's interesting that it started out as a valve that violated all principles, and that's as we knew them at that time. And that's one of the important things that I've tried to teach my research fellows. The way to get ahead is obviously research. It's hard work. Serendipity sometimes helps. Serendipity is, of course, that elegant word for good luck, but the more research, the more hard work you do, the more good luck you do. But the important leg of the three-legged stool is heterodoxy, challenging the accepted beliefs, because all through this story we've had breakthroughs that challenge the accepted beliefs of the azygous flow and the bubble oxygenator and the tetralogy flow and the various valves that we've talked about. So that's a set of principles that is as valid now as it was 1,000 years ago, I guess.
It's a great concept and a great thought, I think, for us to end with, if that's, unless you have any other subjects.
Well, no, I think along that line I try to teach, and we still, I'm medical director of St. Jude. It's a great position for an old professor, because I'm still a professor of surgery emeritus back in Minnesota now. But so I see a lot of young people in research, but those principles I think are very important, and I always say that what you can dream, if you're willing to work, science and technology can achieve, and all you have to do is do the work.
What do you think the place for the minimally invasive techniques of?
Well, I think it's here to stay. You know, there's a tremendous number of ideas now from all directions, and some of them are good, some of them are bad, but I think minimally invasive is here to stay, and where you can do those operations, and some can be done very adequately with equal or even better results with a minimally invasive incision and a more rapid recovery, that's progress. Some of the others I think will fall by the wayside because they don't seem to be able to achieve the desired results. But one of the other things that I've learned in the research of 30 or 40, 50 years was there's no monopoly on creativity in any one medical school, any one region of the United States, any one region of Europe, or any one region of Asia. Young people have creativity if you give them an opportunity to work, something material assistance and stimulation. Because we saw people from in our residency program, I think we trained about 147 in the years 52 through 67 at Minnesota and some more in New York, but they came from all parts of the world, as remote as Vietnam and Afghanistan, and given one of the great advances of that period. I don't try to go into a number of the advances, but one of the important advances in the 60s, early 60s, was hemodilution. That was an invention of Nazi Zudi. Zudi had his training, he was born in Beirut, Lebanon, had his medical school there, and he had his surgical training 2 or 3 years there before he came to the United States. He ended up with us. And his experimental problem in the laboratory was a substitute for blood. You know, in the early days of open heart surgery, as you know, we felt we had to collect 6 or 7 or 8 or even 10 bottles of venous blood from a separate donor, each one from a separate donor, and collect them in heparin rather than citrate, and be fresh for clotting. And Zudi found out that 5% glucose to fill the pump oxygenator and fill all the tubing was not only extremely available and cheap, but it worked better because the hemodilution with hypothermia, you had better circulation during the procedure than you had with normal human blood, and the glucose came out so rapidly in the next hour, 2 hours after surgery that there was no problem. And therefore, the logistics of doing widespread open heart surgery was extremely simplified because you didn't need any special blood collected. You could use the ordinary bank citrated blood if you need replacement, and also techniques for recovering the blood were developed simultaneously. But hemodilution has become a part of the picture so complete. I ask students sometimes about hemodilution. They have a blank look. They said, well, it hasn't always been around. I said, no, it hasn't. So that was a contribution from a person that had his upbringing in Lebanon. He went back for a couple of years, but strife there was discouraging, and he's now head of the Baptist Medical Center in Oklahoma City, a very important position, very important hospital.
Yes. Well, I want to thank you for taking the time